Having breakfast? I'll talk first, right? Just. About? Oh no. Shit. I can advance the slides, but I cannot move them backwards. You know, I can advance, but I cannot go backwards. So, yeah. I don't know if this is normal or what. I can advance the slides, but I cannot move them backwards. You know?
On the clicker?
Oh, with the keyboard. With maybe the clicker works? I thought the clicker.
Oh,
You know, I can move back. But I cannot move backwards, you know? And the clicker.
seems like the right button is still pressed somehow.
Minoves, yes, pretty much. It's a Catalan surname, so it's Minoves. Yeah, perfect. They're from Mexico. Yeah. It's Catalan, you know, is quite close from Spanish, so the pronunciation is more or less the same. Really? Are you busy? No. Sure. Yeah, I belong to UPC. Well, my institution belongs to UPC somehow. They are our. I know. A guy here, not from the networks department, from the audiovisuals department. I think they have some project with the oceanography department. You know, for streaming the sound of the I would say whales or dolphins or something like that. I don't remember. Okay. Wow, he must be busy then. Very interesting.
Bye.
Perfect. Perfect. Thanks. Great. But don't they have to put the survey to the booth? Because if not, how do they get the sleeves? easier. I have a map of the beginning we try to calculate. So.
Okay, so let me do the quick introduction.
Go.
You got your slide.
Okay, we should get started. Good morning, everybody. I think we should get started. I'm sorry, I don't have a microphone, so I will speak as loud as I can.
You have one.
Thank you. Okay. My name is Anna Hunsinger. I represent Internet 2 from the United States, but I'm also a member of the program committee. So I welcome you to this session. The title of the session is Bandwidth on Demand / end-to-end. And we came up with that name to, and as you can see in the abstract, bandwidth on demand is really one component in an overall array of ingredients, if you will, to enable the set of capabilities that can support researchers and the science that require the use of our networks. So today we will have a number of great presentations that will talk, of course, on bandwidth on demand, but that will probably provoke quite a bit of discussion too in terms of some of the issues and approaches when trying to talk about not just what you can do with bandwidth on demand, but again, the whole in support of researchers and science. We have three extraordinary speakers. The first one is Pau Minoves from the I2CAT Foundation. He's also the project manager of Manticore, the Manticore development effort that he will also talk a little bit more about that. We next will have William Johnston. Bill, also known as Bill, is a senior scientist and advisor to Esnet, which is also the network of the U.S., the United States Department of Energy, and the Office of Science within the Department of Energy, and it's the network that supports that organization. He was also the lead of Esnet from 2003 to 2008. And then last, we will have Steve Cotter, who's the current lead of Esnet. Steve was previously at Google, and then prior to that, also at Internet 2. And he will be our last speaker. We have a very limited time, so each of the speakers will have some time at the end of their presentations for some questions. So we ask that you help us also as we get to that part to keep everything on time. With that said, our first speaker is Pau.
Should use this, I think.
Yes.
Okay. Better? Yep. Thanks for the presentation. So, as Anna said, I'm the technical manager of Manticore, which is an FP7 project. I will have a quick overview of the use cases we want to cover. Out. It's better. Okay, great. The Manticore project I'm going to present here is the third edition of a series of projects. It started on 2008 as a proof of concept for trying the IP networks as a service paradigm. It was a private initiative that later evolved to a full consortium. Okay, once the proof of concept proved to be valid, we strived to improve the capabilities of it, and we also ended delivering something that the three end-to-ends, in that case Nordunet, Rediris, and HGNet from Ireland, could pilot. Okay, the pilot was very successful, but what we found out is that the Manticore strives to serve not only to the users, not only to the network operators, but also to the users. So it was a need to look for actual research communities that could use the flexible networks paradigms, or IP networks as a service. This led us to present a proposal inside the Virtual Research Communities objective as an FP7 that got funded and started this October. So we are quite in the beginnings of this project. technical details apart, right now the Manticore consortium is formed by three NRENs, Esnet, Nordunet, and UniC. I took at Essex and Trinity College of Dublin provide expertise in different research areas. For instance, networking, the marketplace, and the grid cloud computing arena, which I'll go deeper later. And then we have Telefonica as business partner. As a quick overview, to do what we want to do, to cover our use cases, we need to integrate services at 3 layers. We have the optical layer, we have the layer 2 with MPLS and Ethernet services, and we have the layer 3 where the IP network as a service itself resides. We do want to deploy an operational service. In fact, from month 10 of the project, we are already deploying something that the users can use. And from there to the month 30, we will be increasing the features. We also have 2 J arrays, one called on the marketplace, where people can trade network resources, and another in the carbon neutral infrastructures, which I will talk later. Yep. So our 3 core communities are the Grid Island Club layer, as we said, the JENet and Ultra High Definition Consortium, and the UniC that provides hospitals and health institutions as a use. Okay, they all can use IP networks as a service in different ways. Okay, you will see that the Manticore tool is the same, but the way it is used, it changes. From these 3 use cases, we have developed. From these 3 user communities, we have developed 4 use cases. We have distributed and private clouds, media or ultra high definition bandwidth on demand, and the virtual CPE as core use cases. And then we have Green IT and marketplace as J arrays. Okay, you can see that all these 5 use cases are enabled by IP as a service paradigm, which in turn is enabled by bandwidth on demand. First use case is the virtual CPE. In this case, we have UniC and Esnet. They have CPEs at the ends of their networks. You know, this CPE is sometimes part of the NREN, sometimes it belongs to the client, sometimes it's something mixed. The idea of Manticore is that it allows delegation of partial configuration rights. So everything you can configure on a virtual infrastructure, you can delegate this right. Okay. Manticore should allow, for instance, the NRENs to allow clients to configure via RRP or the internal routing protocol, but block them from touching, for instance, the BGP configuration, because this is something that affects the internal stability of the network. Also, we do support a lot virtual routers. We make a lot of use of that. In fact, Manticore users don't distinguish between a physical and a virtual router. Okay? The idea is that we can reduce the need of hardware by allowing to deploy logical configurations instead of logical physical new setups. In the same way, we can have a CPE that serves only one customer, but this customer wants to enter new international testbeds on demand. The idea is that we want user-driven, so the actual doctors or IT departments can have an interface to ask them to be aggregated to an international testbed. And Manticore should move the network and arrange the setups, be a virtual router's MPLS path or optical light path, whatever it needs, to aggregate this network to another testbed. The idea is that the IT department of the NREN will only get involved in the case that things go wrong. So if the provisioning is actually possible, it's fully user-driven. The same way, and depending that there are some CPEs that have different physical access to the real network, the same setup should be possible via layer 3 VPN. The distributed and private cloud, as we said, has 2 scenarios, and is one of the most complex we have. In this case, we have the Grid Island, which they have some 10th of grid sites. Grid site is composed by infrastructure nodes and worker nodes. And the workers nodes, they are private, they reside inside the LAN, and nobody can see them from a network point of view. And infrastructure nodes are the only ones who have internet connectivity to the rest of the grid sites. So the federation of grid sites is a bunch of infrastructure nodes that they see each other across the internet, and in this case, across HCINet layer 2 network. What we want to enable is all the worker nodes to reside in the same cloud, so they get added on a layer 2 perspective to a single grid site. So you have a grid site that spans across all Ireland, and a single set of infrastructure nodes see all the worker nodes as if they belong to the same network, okay? As a first step to a cloud paradigm. Furthermore, we want to remove the infrastructure nodes from the same site and allow them to be distributed among all the grid sites. On a first approach, we will do this at layer 3. Why? Because the customer, so to say, in Manticore, here may be a university department or a hospital department that has some computing resources and is not necessarily in charge of all the network between him and the people he wants to collaborate. So there are a lot of IT departments involved that may or may not collaborate on this. So the first approach is to do this at the layer 3 VPN, so you can jump among them. The second approach is to get the actual infrastructure involved and do the same at the layer 2. So we can actually provide distributed high performance computing. It's something that the best effort network as internet cannot do. Another scenario of the same use case, you will see that the technological substrate is the same, but the users and the way they use it, it's different. We have campus, so universities, we have an NREN in the middle, and then we have a computing resources provider, so data center provider, which can be the very same NREN or can be a commercial operator that's directly plugged to the network. The idea is that campuses and universities, they want to move computing resources out of the network, so they wanna go cloud. They don't want to take care about data centers anymore. Okay, they want to buy infrastructure as a service, but they have huge legacy systems they cannot reconfigure at network level, okay, because that's too costly, and most of the times they don't even know how many things can break in a migration like this. So we want to enable them to move things to the cloud, keeping the same layer 3 configuration. So what we actually have to do is to span the network all across the NREN to the final data center provider. In this case, we will do this via a layer 2 MPLS full mesh network that NordNet provides, well, in this case, Esnet. If you are familiar with the Amazon Virtual Private Cloud, you will see that it's mostly the same approach. Okay, there are some key differences that I want to highlight. So it's nice to see that the commercial operator sells the same concept. So it's kind of a backing up, but by their position, they have to serve customers across the internet because this is where they are. But we can take advantage of being directly plugged to the NREN. Most importantly, well, they offer a mix of templates, whether you have a private subnet, a public subnet, you have both, etc., etc. But the thing is that they provide a layer 3 tunneling. They can help you keeping the same address space because you can put layer 2 inside that layer 3, but you always have a tunnel across the internet, so it's best effort, so it quite limits what you can do with that. What we want to provide is a layer 2 pure solution with QoS and guaranteed bandwidth, which offers a lot of new possibilities. For instance, grid sites, when they compute, they really need to move big chunks of data, and they cannot rely that the internet will take all of that, or they cannot pay for a connection with that quality across the internet. We will also support IPv6, which is something that interests the NRENs a lot. And we will not only provide the service, which is what we do inside the project, but we take a lot of care of producing an actual tool set that anybody can take, as any other open source project, and try and install at home. So with this solution, you should be able to offer the same service, just throwing some technicians to it without actually need to be inside the Manticore consortium. The last use case, and it's maybe the most bandwidth on demand pure use case, it's the ultra high definition consortium at Essex, Glasgow, and Cardiff. They need to stream 3D stereoscopical data and medical applications. Manticore needs to take care of that use case too, because it's quite foundational. Evolving that bandwidth on demand use case, we have the marketplace, which is where the University of Essex had its main research area. The idea is to taking this delegation of configuration rights capabilities that I have explained it before. The idea is that you can use that to actually sell networking infrastructure. So there is a marketplace where network providers and NRENs or physical infrastructure providers can publish the resources they have and the resources they can create. Because if you have a big router box well placed with good connectivity, you can actually sell the fact that I allow you to create a virtual router inside that box. And you can somehow define which kind of virtual router you need and which interfaces you need it to be. Okay, this is the marketplace paradigm. We have some research, well, this is actually a JRA, on the necessary algorithms to allow for that, for the source publishing and the offer. Because the idea of the marketplace is that it offers you, not it doesn't deploy what you need. It offers you some solutions, and you can see the cost of each solution and choose what you want to get deployed. To do so, well, Manticore will interface with a lot of components that actually know the network substrate. We will have to emulate that network topologies that offer different costs for the same provisioning of network. So you can choose. For the Green IT area, we collaborate with the Green Star Network project. They have an international testbed of data centers that spans, I would say, mostly the globe, but I'm quite certain they have all around. From the network associates area, there is the European area where there are, I would say, 7 data centers where Manticore provides 6 of them. We can see, for instance, the 2 that we have in Ireland. They are solar-powered and wind-powered data centers. The idea of the Green Star project is that you migrate computing resources from one data center to the other as the solar and wind energy falls and goes up. Okay, so this is very interesting from a Green IT perspective, but it kind of put a lot of challenges in the networking area because the system cannot be interrupted, so the IP connectivity needs to remain across data centers. You can see it's another VM migration issue in another domain, and Manticore should take care of that too. Just for the record, a node in the Green IT area is basically an undefined amount of computing resources, Ethernet switch, and an optical patch panel because the test bit is optical. In the PDU, it's connected to everything, and it's a special PDU that it allows us to know which device, how many amperes each device is consuming. This information is published via IP, so Manticore can connect and gather the information for all the networks. Manticore account this data and should be able to tell you your IP network, whether if it's physical or virtual, how much it is consuming. Okay? As a future research line, it would be interesting also to make that accountable, so people can pay not only in dollars but in carbon credits. Well, this is a view of the world network and the ones that belong to the European area. So, I think I'm pretty much done. This is the Open Project website. I think this is quite innovative from a FP7 perspective. We work a lot quite an open source project, so you can join the mailing list where much of the discussion happens. There's an open wiki, and in fact you can get the software. I would advise you to wait until 1.0 to get the software if you expect it to compile, but good news is the 1.0 should be available in a month or so. So a minimum set of the functionality will be available very soon. If you are familiar with an open source project, that's pretty much what you can expect. You can also see the archives with all the discussion happening. I don't know how many projects allow you to see the discussions of everything. Also, you have found some surveys on your chairs. We have iPad sleeves and laptop sleeves available at the AutoCAD booth for the first of you who fill up the surveys. I can say there are more surveys in this room than AutoCAD sleeves, but we have many. We would like a lot to hear your feedback because these are our core use cases. They vary a lot, but we feel that there is a lot of people that could use them or that could use a slight modification of them. So if that's your case, please come to our booth. We would love to hear your case. Also, for more long term, you can join the mailing list. We are, I think booth is number 9. It's between Giant and Ripe. And the survey is online, so in case you don't have the paper, you can just click there. So I'm done. Keep on schedule. Yeah. If anybody has any questions. Thanks.
Yeah, I have a short question to your last
Sure.
Stuff. According to the Green IT, I'm not sure if I understood it well, you mentioned that either you got the energy from sun or from wind sources, and regarding to that, you are moving your data and whatever from one center to the other. I wonder, what is the rationale to move the data from one center to the other instead of moving the electricity from one source or the other to the data center? I mean, to have two data centers just for moving to each other is very expensive. Instead, should have just to move the electricity.
I don't know if the Green Star project use case is to have to expect companies to have data centers across the whole globe. I mean, I understand that few companies can afford to do that, but most of the companies just buy computing resources from external companies, and they can have several providers. For instance, they can have providers in the States or providers in Spain, where there is a lot of sun, for instance. And when it goes dark in the States, it goes up, it rises the sun in Spain. The idea is only to migrate the VMs to one place to the other. Of course, you can, if the sun is down, you can plug it to the grid and take grid power from now on for the whole night and save from the migration. But the Green Star project has a lot of advance in the green carbon credit market. So they expect that if you plug energy from the grid, it may cost the same or maybe even be cheaper from a dollar perspective, but you will get carbon credits charged. So if you want to save these carbon credits and you can do the same computation in another place where the energy is free in the carbon credits. For instance, one of the nodes is on Iceland. Energy there is quite cheap, but also it's carbon credit free because it's all geothermal. Okay. Well, yeah, moving the energy from one country to another is usually not an option, of course.
Well, even that, I mean, what you'll find is that the power grid is not symmetric. You can't move a major generation source arbitrarily from one place in the power grid to another. We saw a major wind energy project in the state of Texas fail because they couldn't get the energy out without building new transmission lines. The power grid is, it's a last mile problem. The power grid is designed to do a huge fan out, and you can't start at the leaf node and pump a lot of power back into the network. It doesn't work that way.
Not only that, it's also very difficult to move energy, but also green energies like solar and wind, they are very good because they can provide distributed energy, because you don't need a huge nuclear plant, but they provide low energy. So it's very good for ICT, where you need a computer or a data center. A small data center doesn't take up a lot of energy, but it needs to be in a lot of places. You cannot put all the data centers in the same city. So it kind of fit. We think the paradigm fits a lot for the challenges that energy distribution provides us. So that's it.
Well, thank you, Pal.
So I see somebody navigating the screen, so I guess we'll get my slides up in a second. Is this the changer? Okay. All right. So this title is wrong. The title of this session is wrong. And I was talking with Jean-Luc Durel, one of the Framework 7 program managers, and he pointed out to me that what we're talking about here is not so much bandwidth on demand as topology on demand. And I'll make that point as I go. So briefly I want to say, it was mentioned that the Esnet serves the Office of Science, and the reason for that is because the Office of Science funds a great deal of, like 45% of the physical science research and instruments in the U.S., together with the National Science Foundation. Let's see, what do I aim this at, because it has quit working. And so these projects and instruments have the characteristics in common that they share a huge amount of data. They have many collaborators. All new large-scale science projects have large collaboration communities. They have to do distributed data processing, management, distributed simulation, et cetera. So very briefly, what Esnet is it's a full-service network. The thing that is that is distinctive is that Esnet for some time now has been designed as two separate networks, the dark blue and the black, to precisely to address the problem that Case pointed out in part of his talk, and that is to separate the large data flows from the small or commodity data flows. They just are not compatible. So most of the bandwidth is in the dark blue network, which is designed to handle the large-scale data flows that science generates. Esnet's big. We're a small organization. The United States covers a geographic area that's indicated there. I always put this up when I come to Europe. You know, we only have like 30 people in the organization. We're like, you know, a small NREN staffing-wise, so this is a challenge. By looking at the network traffic, there was a fundamental change in the character of the traffic starting about mid-2005. And the tops of these bars that you see marching up are the fraction of the traffic that's in roughly the top 1,000 flows in the network. There's some 1.5 billion flows per month in the network. And this is essentially the arrival of large-scale science becoming dependent upon the network. And so these top 1,000 flows are the gigabit per second, sustained gigabit per second flows of large-scale science. And for those of you who saw Case's talk, you know, the LHC is the current big example of this. There are two major detectors. These detectors are essentially 10,000 pixel three-dimensional cameras that operate at 40 megahertz a second, instead of 30 frames a second or whatever a typical video camera operates at. The result is they generate huge amounts of data. The data is analyzed in a divide and conquer, flows from top to bottom. At least that was the original concept. However, that original concept is breaking down. And so now we're getting a lot of chaotic lateral flow where people essentially go anywhere they can find the data instead of to their designated Tier 1 data centers. The Tier 1 data centers in aggregate hold a single copy of an experiment's data. And CERN holds an archive copy on tape, but it's not accessible. So for CMS, for instance, the entire CMS data set is scattered across 12 Tier 1 data centers. The way that this is done is as follows, and this is interesting. This is the PanDA job management system manages the analysis jobs for the Atlas experiment. And it is essentially a grid job broker. And so what it does is requests for jobs come in. They're queued in a task buffer, and then the job broker's responsibility is to do two things. First of all, find available resources. And the available resources are the Tier 2 data centers. There's some 30 of them in the US. Oh, thank you. There's some 30 of them in the US. And each one of these will have anywhere from 1,000 to 10,000 cores available, and anywhere from of order a few terabytes of local disk storage. And so these tier 2 data centers report back to a grid scheduler what their current availability is in terms of their job load. That reports back to the job broker. So the job broker, the next thing that the job broker has to do is to invoke the data service, which is currently a piece of software called DQ2, which is a big elaborate system in its own right. I haven't opened it up. DQ2 locates the best copy of the data and then organizes third-party transfers through the DDM agents to the data center. And so once the data starts to flow into the data center, then the job dispatcher triggers the job, and that's how the analysis is done. So there are critical paths here and here and here for control, and here for the data movement. And I say critical because if any of these paths breaks down in terms of communication, then this whole system, which flows data continuously, and the goal of which is to keep every one of these cores available, operating, doing computing all the time. Because the total size of this is pretty well sized to being able to analyze the data that comes out of the Atlas detector. And so if you lose very much time in any one of these, you won't be able to keep up. Even if the network is, say, one of these major data paths partitions, even if the network could catch up, there isn't sufficient time on the in the tier 2 data center processing environment to catch up after the fact. This is a production system. We're talking about running essentially terabytes a day through the processing farm in aggregate. They have since the current run started up, moved about 7 petabytes of data in total between the centers. So this is about as large a science experiment as operates anywhere. Characteristics are actually fairly consistent across most of the large-scale science projects that we've looked at in some detail, and they use distributed applications to couple together existing pockets of code data and expertise into sort of systems of systems, break up the task of massive data as analysis, as I just described, and then they distribute it and manage data globally. And so these application systems that do this are data intensive, high performance. They have very high duty cycle for the reasons I just described. They're widely distributed, typically spread over continental or intercontinental distances, and they're built and used by global scale collaborations. Characteristics that we have identified are bulk data transfers with deadlines. That's effectively what I just pointed out, that you have to keep the data moving continuously in order to keep the available CPU operating. You have to support reliable inter-process communication, again, so that the system will keep operating. You have a big complicated workflow system, and you disrupt something down in the middle, then that whole flow of work to that part of the system backs up and slows everything down. We have use cases for remote instrument control and coupled instruments and simulation, but they have not seen the production kinds of use yet. They will over the next few years that the LHC has. Also, there's a lot of interest in remote file system access. That's being done some now, but mostly in dedicated private networks. So we really don't have a lot of experience with it yet, but that will also come. So the network as a service, so the distributed application system elements, such as the ones I described for the Atlas data management, they have to be able to get guarantees from the network that there's adequate bandwidth to accomplish what they have to do in adequate time. And they have to get real-time information back from the network in order to allow for graceful failure and auto recovery of the applications themselves. And then, of course, all of the services, all these big science applications are built essentially in a web services paradigm. So that's where the service has to be available. So OSCARS is a service-oriented virtual circuit service that the Esnet has been developing for a number of years now. Twitchy. It essentially allows you to specify reservable bandwidth in a time slot. Explicit backup paths may be requested. I'll comment on that later. This is where it starts to look like a topology on demand service. The paths are either layer 3 or layer 2. Almost all of the large-scale production paths are layer 2, and then the sites put their own routers on the end of it, constructing an L3 VPN. And of course is available in the web services framework. It does do traffic isolation, and so it is possible to, even though you're mixing this on the same router interface with commodity TCP traffic, it isolates this traffic so that you can use non-standard transport protocols like the demand-driven UDP protocols. The connections are secure. They're managed by the core routing infrastructure of the network, and so to the extent that you can maintain control of the control plane of your network, which most network organizations are very careful about, then the circuit is secure. And this enables a variety of traffic engineering types that I'll comment about. Originally, the bandwidth requested was treated as a fixed and immutable constant. And what we found was that wasn't really the semantic that people wanted to use. They really wanted to be able to burst over their allocated bandwidth if that could be done in the right circumstances, so that if the path has idle capacity, that they can make use of it. I'll point out the reason for that in a minute. And then they wanted to provide somewhat different semantics on different types of paths, so that you could request a circuit as a backup service, but not necessarily have it guaranteed in the sense that you reserve 2 solid circuits with the same amount of bandwidth, since that would obviously constrain the remaining available bandwidth in the network. The environment, of course, is inherently multi-domain, and there's been a fair bit of effort particularly in the international community between the U.S. and Europe, and some with Southeast Asia, to ensure that interdomain circuits of this type are possible. So the capabilities that make up OSCARS, the switches and routers have certain functionality that's available, and you really have to make use of this functionality. For the kinds of data rates we're talking about, most of what you're trying to do cannot be done in software. It has to be implemented the switching functions, the routing functions have to be implemented in hardware. You need multiple levels of queuing to manage different classes of traffic. You don't need a lot. 4 is sort of the standard. The low, which is sometimes called scavenger traffic, best effort, which is where all of the regular TCP traffic goes. There's an expedited class, and that's what we use for the OSCAR circuits, is the expedited class. The flash class is generally only used for network management. It's not used for any user functions. You need to be able to shape the traffic somehow to the specified bandwidth in order to do resource management of the overall network when you're allocating circuits among a large number of people. We allow for the possibility of layer 3 only access to OSCARs. That's not used very often because most large institutions have multiple physical connections, and if they're generating a lot of data, they'll have their layer 3 IP connection, commodity IP, and then they'll have a multiple layer 2 connections for the data. But some sites don't, and so we wanted to provide for a layer 3 service, and this amounts to a policy-based routing at the edges. Ethernet VLANs already provide a pseudo-wire service, as does MPLS. So those are the tools that we have to work with. The standard capabilities that are used is we use OSPF-TE for topology discovery, and by topology discovery in this case, what I mean is the topology of the underlying physical network that we use for determining what resources are available to the system overall. And then we use RSVP to signal the paths through the network. What I haven't said yet, but which is probably obvious, is that this is all MPLS based. So to these tools, what we do is we add reservation commitment management. And so all new paths that are found through the network to answer a circuit request have to take into account all previous commitments for circuits so that you don't oversubscribe the network. You know, the whole key to this is the part of the network that's allocated to the circuit service cannot be oversubscribed because if you oversubscribe it, then you can't guarantee bandwidth. And so this is essentially a pathfinding problem. We use strong authentication for reservation management, and there are hooks in there to do authorization in order to enforce policy resource usage. At this point, that's being done manually rather than in an automated way. As I pointed out, we decided early on to use both layer 2 and layer 3, and we also decided early on that we would not require TDM equipment in the network. In other words, we're not going to install a lot of new equipment to provide something like VCAT, LCAS managed bandwidth channels. This is all going to have to work with the layer 2 and layer 3 devices that were in the network. So OSCARs is a virtual circuit service. It provides backup guarantees, bandwidth guarantees at specified times. It's capable of communicating with similar other services, and it clearly separates the network device configuration module internally, so that OSCARs is effectively a control plane for circuit management. We use MPLS to produce the circuits in the, within the existing network. You can plug other modules in there that, for instance, manage a SONET network, and people have done that. So I'm going to skip that. So what I want to do is to show how this is used for user-level traffic management, which is really where the topology on demand comes with. And if you have like I said, most of the use of OSCAR circuits are to provide pseudo-wires interconnecting layer 3 routers at the user sites. So if you have a primary circuit and another primary circuit which has a different purpose, and a third circuit which you've set up paths that are of limited bandwidth because they are designed to be backup paths for these primary 10 gig paths in this case. Plus, there's another use of this circuit. Say in the case that I'm using here, it's actually, this is the circuit that carries the commodity traffic out of the site. And so by specifying these two circuits and then assigning BGP weights to them in the user environment, then if this circuit fails, then you can potentially get 8 or 9 gigabits out of this circuit, because the burst traffic over 4 gigabits, which is what's guaranteed, is marked as low priority. It's marked as scavenger traffic. And so if there's only a gigabit per second being used in the commodity environment, which will be standard priority, then this circuit backup path can effectively get 8 or 9 gigabits per second as a backup, and similarly for this one. And so the site can essentially craft its own use policy in failure modes. And so as each of these different paths fails, the site will decide what is the available reuse capacity that I want to dedicate to a backup path. So this is why I call the Oscar, or why I say that Oscars provides effectively a user level traffic engineering capability, which I just said. The software itself has been under development for about 4 years now, and the software itself has evolved substantially. In its latest incarnation, there's a collection of functions. This is the device driver, the path setup piece I was telling you about, and this is where in Esnet's version of Oscars, this is an MPLS management system. But the core computation, this does the basic constrained path computations, looking for a path through the network that has the available bandwidth, not just now, but for all into the future, all the way up to the point where the last extant reservation exists. There are then authorization, the resource managers, there's a broker notification, and then there's a naming service and a topology management service. These are now all completely independent modules that use SOAP and WSDL as communication, so that people can pull any one of these out. That is, if somebody besides us takes this, if they want to use a different pathfinding algorithm, for instance, they can pull this module out and replace it, because these interfaces here are being standardized, and this is part of what's going on in the NSI community and the grid forum. These two modules have already been essentially, they're just stubs now. They've been seconded to the corresponding lookup service and topology management service within the PerfSonar suite of network monitoring tools. So the software, even though it's called 0.6, in fact, is on its third complete rewrite to produce this very modular approach to the overall system. This is the result of the interoperation is the result of a collection of folks getting together in an ad hoc way to produce a protocol that these interdomain controllers could talk to each other, and that's handled down here. That is, user requests from other IDCs come in, so that you can do pathfinding not just within here, but across several of these, because you're traversing different network domains. And that's what's sort of expressed here. So here you have the IDCs, you have the protocol for passing topologies around and finding paths through the multi-domain network. This is, there is a group of people that have this interoperability, and the next step is that these protocols will move into the glyph and the grid forum environment, so that a larger group of part of the community can look at them and decide where things should go from here. Oscars is a production service in the Esnet. Almost all of the services are long-term services. They're not bandwidth on demand. They're essentially topology on demand or topology management services for a number of big science projects. Most of it is in the LHC, but we have some supporting the climate community within the U.S., computational astrophysics, biology and environment. The LHC is the only one which is international at this point, but these are all multi-domain. This is the short reservation, and most of it's used for experimentation and things like supporting demos at supercomputing and other conferences like that. There have been tools built. This tool was built to help site managers, site network managers figure out or keep track of the circuits that they've set up and where the endpoints of the circuits are. And so these topology diagrams are generated daily and made available to the site managers, and they give the details of which interfaces are being used for what circuits on which devices in the network. So this is a network operator's tool. We have integrated Oscars we use the Spectrum. It's a commercial monitoring system to monitor all of the equipment in the network, and the Oscars circuit service now looks like another device in the network. And so this is just what the operators see on their console when they're trying to manage Oscars. And so there are, as I pointed out, there are a number of projects funded to work on the development and generalization of the forward direction of this sort of circuit service. That's it. Any questions?
Any questions for Bill?
Hi Bill, this is Gerben from SurfNet.
Hi.
I'm glad that you mentioned OGF's NSI at the bottom of this sheet, because I noticed that you were focusing a lot on the IDC protocol. Do you think that for Oscars, NSI is the way to go here in the inter-domain communication?
I'm sorry, do I think Oscars what?
That NSI is the way to go here forward?
Well, Oscar, it was the DICE collaboration was a small group of people that wanted to produce a proof of concept for the interdomain circuit services, which at the same time was useful. That has been done, okay? And it's time to open up the idea to a larger group of people, hence the work with the grid forum, the NSI group, to try and say, look, here's a service which is useful. Here's a prototype, multiple prototype implementations that interoperate. There's at least 3 or 4 different code bases. I mean, Oscar's code base is used in probably a dozen different networks, but there are at least 3 or 4 completely independent implementations of interdomain controllers. And so this is a very powerful statement of the fact that yes, it's useful, yes, it's doable, and here's the first cut at it, and then from there the larger community will move forward. Do I see any fundamental changes in the semantics? I don't know. I'm not sure what one would add to this essentially topology on the demand virtual circuit service, but remains to be seen.
You got Inder over there too.
Hmm?
You got Inder over there. He's leading that working group.
Yeah.
But there is a talk on NSI this afternoon, so
There is a talk on NSI
Yes.
this afternoon, so I think
I would point the people to come to that talk.
Sure. And I should point out, incidentally, to plug it should be clear, to plug an OpenFlow switch into this as a device will be very easy, because particularly with the MPLS module that Oscars uses currently, that's effectively what's doing. I mean, RSVP configures each router along the path that it computes independently. So MPLS TE is not used because the traffic management, the circuit management is too simple. So if you substitute loading the switch tables in OpenFlow switches, then you've got an OpenFlow switch module. Anything else? No? Thank you.
Thank you, Bill. All right. Now Steve Carr.
Yeah, don't mess it up. Sure. So while he's setting that up, I knew, having heard Bill talk before, that his talk would be very thorough, and that I'd have to think of something different to talk about. So my talk's going to be still talking about what ESNet's doing around bandwidth on demand, but it's going to be a little different than normal. Let's see. Okay for me to take over, or? Okay. All right. I think this goes to, I don't know, I'll leave it at that. Okay. So, what I'm going to talk about is, oh, use it. I can just do it from here. That's no problem. Okay. Okay. Again, I thought I'd try something different using this presentation format. So, I think we've heard that bandwidth on demand can be a great enabler of science, and providing guaranteed network performance can be essential to certain experiments. As Bill mentioned, at ESNet, we've been experimenting with bandwidth on demand since about 2005. We put it into production in 2009. And as Bill said, today about 50% of our network traffic goes across these on-demand virtual circuits. So from that perspective, you could say that this has been pretty successful, and that the capabilities of the bandwidth on demand service have been good enough for what we set out to do. But I will argue that bandwidth on demand alone is not good enough to support the science and the scientists effectively. So I'm going to talk a little bit, give a couple examples where good enough was acceptable for a while, and then we'll see that it no longer was the case. Then I'll talk a little bit about some of the lessons that we've learned after we've deployed the service and had it in the network for a while, and then I'll finish up by talking about what we're doing at ESNet to kind of build a bandwidth on demand ecosystem. So, first example is the Ford Model T. It was called the Tin Lizzie because it was it looked frail, didn't look very rugged. It came out in 1908, but it was a huge success. Ford sold over 15 million Model Ts over the life of the car. And his invention of the assembly line kind of revolutionized manufacturing. But Ford was a little bit, let's say, overconfident with his success, and in 1909 he proclaimed that there would be no new models, no new motors, no new bodies, no new colors, that the Model T was fine exactly as it was. And he stuck to his guns for 18 years, despite some very obvious shortcomings of the car, some of which were the fact that the driver's side door didn't open. You had to step over it to get out because it had the spare tire there. Also, the headlights would dim at low speeds, requiring drivers to stop in the middle of the road and rev the engine at night so they could see far enough ahead of them that they can drive on. And probably worse was there's no way to check how much gas you had, so you had to actually stop the car, get out, lift up the front seat, and stick a ruler down into the gas tank to figure out how much gas you had left. So I would argue that we have several Model Ts in our community. Software development projects that, for various reasons, we've, whether through a lack of funding or support, have failed to continue to improve and adapt the code to the user's changing needs. So that's the first example. Next example I would talk about is something I think everyone's more familiar with than a Model T. At first, Microsoft developed their code for early adapters, people that were more comfortable changing out the PC cards. Early adapters were obviously more willing to work around issues. So Microsoft developed a model where time to market won out over quality. And because of that, they would develop code quickly, get it to the market, and fix just enough bugs so that it would work. And then, as we all know, we're constantly getting bug patches, and you're constantly having to download, the next round. Was it every first Tuesday of the month? It's almost become habitual, and we've grown accustomed to that and accepted that. I'm not sure that we really should, but we do. So what has happened is that the development code and this model for early adapters didn't last very long. As computers became more prevalent, the Microsoft user base changed, and more consumers began using it. Enterprises started deploying it, and all of which were less tolerant than those early adapters at taking code that needed to be constantly corrected and fixed. So these new users began to value quality over the hassles of experimentation, and the result is, as we've all become familiar with, is the blue screen of death. So rather than what probably they should have done much earlier is instead of taking code and constantly fixing bugs and everything, they should have just maybe thrown it out and started over. And I think Microsoft has started to be able to do that, even though it took a long time for them to get there. And and now, the Microsoft, one of the things that everyone knows them for is this blue screen. So again, I would say that in our community, there are some cases that we're not much different than Microsoft, where we've taken research projects that we've been funded to do, develop monolithic code, and then after the research project's been done and we've done the proof of concept, we then try to adapt that to a production environment and use code that probably we should have taken and thrown out and built from scratch as a production type code. The last example that I'm going to give before I get into talking about what Esnet's done is one that happened just a couple weeks ago and is community specific. What we had was a climate researcher in the U.S. that contacted or had been using a DOE supercomputer in the States to do some of their computation. And so they had 170 terabytes of data sitting there. And they were done, and they wanted to bring that data back to Europe. So they got together, the researcher and the engineers at the supercomputing center, and they started brainstorming, how to get this data back. And they discussed using the network, and the researcher was told by the engineer at the supercomputing center that it would take months to transfer that much data over the network. I think what they didn't realize is that with a connection of less than about 500 megabits, they could have transferred that much in 1 month and not several months. And they also probably didn't realize that we handle flows greater than 500 megabits all the time. So what they did is they ended up buying a disk array in Europe, boxing it up, shipping it to the US. The guys at the supercomputing center downloaded the data, created it back up, and have mailed it over back to Europe. So, we call that sneaker-net at Esnet, right? And so, why did that happen? What caused that? And I think one of the problems is that there's been a history of poor performance of the network at the location that the researcher was at. So there's a very low expectation of what the network could do for the scientists. And there was also an unwillingness, I think, to tackle the tough problems and fix it once and for all. So what they did is they came up with a bypass to the problem. And so the point I'm trying to make in this talk is that we've come to accept bad performance as good enough, and we either find ways around it or we just accept it the way it is, and I don't think that it necessarily needs to be that way. So what we found in talking to our scientists that we support is that poor network performance is often the norm, even in a backbone network with a lot of advanced capabilities like bandwidth on demand. A lot of the problems actually exist at the site, where the researchers are buying kit that has default configurations and they use tools that aren't optimized for wide area transport. Often the scientists at the sites are left to figure it out for themselves. When they need, when the network doesn't work properly and they have to troubleshoot, often they're left to do it themselves, or they're asked to be network engineers and look at what they're doing and tell us what's wrong. And the end result is that many of them give up and again resort to sneaker-net. So how are we going to get around that? This isn't a lost cause. I think we don't necessarily have to be satisfied with bad as good enough. There are successes in the community. I think the LHC and the high energy physics community is one that is a model. It didn't just happen overnight. They've put a lot of time and resources and money, quite frankly, into incorporating the network into their collaboration model. But I think that as networkers, we also have to take leadership in this, and we have to start by building the tools that scientists can use, and then we got to continue to innovate and improve them. We have to develop services that are intuitive for the researchers, not intuitive for us, but intuitive for the researchers themselves, and then provide them the documentation that allows them to use the services effectively. And never forget that that a lot of these researchers don't have any understanding of networking. They're chemists, they're biologists, and we can't be developing tools that work for us but don't work for them. So as Bill talked about, we've been using bandwidth on demand in Esnet for for several years now, and we've gained a lot of experience and done a lot of internal reflection. And we just wrote a paper that was published in this month's IEEE magazine. In fact, we had 3 papers in there about hybrid networking. So I'll give you a link to our blog where you can read about it. But one of the papers that we wrote about was what were lessons learned in deploying a bandwidth on-demand system. And I think first and foremost, we learned that you need to take into account the network administrators at the end sites and the other networks that you're going to build these circuits across, and not forget that they have an impact. If the LAN administrator doesn't understand what you're doing, they're not going to allow you to provision the bandwidth end-to-end dynamically. We also learned that you've got to abstract the service and put it in terms that regular users understand, so they can pick the sort of capabilities that meet their needs. As Bill mentioned a little bit about setting up redundant circuits. First thing, if they're going to be wanting guaranteed bandwidth, you should know that they're going to want automatic failover. I mean, if it's important enough that they want the guarantees, it's going to be even more important that when the path fails, that it automatically switches over. There are service level expectations that we have to communicate to administrators at the end sites, and so that you get the permissions and understand the restrictions of the provisioning. You also have to understand what is the best layer, the most efficient layer to transport the traffic out. Is it layer 1, is it layer 2, or layer 3? There's different parameters. Layer 1 may be more energy efficient. Layer 2 and 3 offer other advantages. And we also learned in deploying this that you have to make the reconfiguration and changes visible to the user. Science is going to want to know if you change this path for whatever reason, why, and when it happened, and for how long it's going to stay that way. The last two, obviously, you've got to have monitoring capabilities in there, so that often you don't have clear failures, but you've got soft failures or degradation in performance, and you got to be able to monitor it and be able to correct it when it happens. And you've got to also make sure that you have a way to do resource brokering and co-scheduling if you're going to offer us as a infrastructure as a service type model, which we've actually done between the Joint Genome Institute and one of the supercomputers at DOE, and in 1 month transferred over a petabyte of data. So Bill mentioned that we just did a complete rewrite of Oscars.6. Some of the things that we made sure that we did, and this took a whole year and a half where we essentially threw out the old code and started over. And Bill touched on this a bit. We made it completely modular. We designed it to be production quality from the start, and we also made sure that we clearly defined APIs. So as Bill mentioned, if someone wants to pull out a path computation engine that, say, incorporates, looking for a path that's most carbon neutral, you can do that. And so it's a plug and play with the APIs. Another thing that we did is we, for the first time, built a dedicated test environment to do rigorous testing of the code. And we're actually, we finished the code in April, and we're currently doing the testing now. And we would welcome anyone that is interested in helping us identify bugs and play with the code to just let us know. We're happy to have more people look at it. Another lesson that we learned is we've got to define and stick to the schedule, right? We've gotten more systematic, and we've identified engineering commit with features and dates, and we stick to that. And lastly, now that the code is done, what we're going to do is sit back for quite a while and just observe how the users use it. It's very often when you develop something with a particular idea in mind that when you finally release it to your user base, that they do things with it that you never even thought of or even considered. With Oscars, as Bill mentioned, what we originally thought of as a bandwidth on demand capability where a researcher would make a reservation, send their data, and then release that bandwidth back into the pool for the rest of the community to use. What we've actually found is that they use it more as a traffic engineering tool. They put their virtual circuit up and they leave it up. And that was not something that we originally anticipated, but we again had to adapt and added the ability to burst over the reservation. So now what we basically offer is a minimum amount of bandwidth, a guarantee amount of bandwidth. And then if there is available capacity, then they can burst over that and get greater throughput. But we found that they very rarely will release their reservation and put it back into the pool. So thinking a little bit further, how do we enable the scientific use of these bandwidth on demand networks? Developing a technology is fine, but that doesn't mean it's going to be a useful service. And so one of the things that we've been actually putting into practice is building a simple enclave for these data-intensive services. And we've done this at several of the national labs, and we have a couple others that we're working with right now to help them redesign their networks. The idea is you put this enclave close to the site perimeter. It has a separate security policy, because as we know, security is it's important. You can't ignore it, but it also will throttle the scientific data if you have to push everything through the same firewall that your voice over IP and email is going through. You're not going to get too much through. And by separating out, the data network from, the converged network services, you don't have to deploy as many switches and routers with deep packet buffers because they're expensive, and you don't necessarily need them throughout the entire LAN. It also makes it a lot easier to debug for the large flows if you aren't having your science traffic going all the way through the entire WAN and all the switches and that have other lab traffic or site traffic on it. So we call this this enclave a science DMZ. And what we've done with these labs is we've built these well-configured locations for optimized for high-performance WAN science services. It's typically on dedicated infrastructure, but it doesn't necessarily have to be. You can do it virtually. For example, with Oscars, we can do it where we can isolate the science traffic, with our virtual circuits. We put dedicated high-performance data movers in there. And we fully instrument the Science DMZ enclave with per sonar, and we put an IDC in there, so inter-domain controller to do the provisioning. And so we're able to send the science traffic across a wide area without having to traverse the LAN, and these allow the large flows to move unencumbered. So if you look at a very simple diagram of what we're talking about here with the Science DMZ is you have in blue there, so you've got the site border router, all the traffic from the WAN comes in there. The science traffic gets routed to Science DMZ, and then we have a high performance transfer node, so if we want to send it back out, we can use that. It's fully instrumented with per sonar. You can set security policy just for the science traffic. Traffic that is destined for the rest of the campus goes through to a border router and the firewall there. If you need to move data back and forth between there, you can. But this is the idea in a pretty simple diagram of what we've done with the Science DMZ, and it's been pretty successful and greatly improves some of the throughputs that we've had. So this is part of what we've been talking about is building the ecosystem around these services. And so at Esnet, we've set up an environment where we're trying to make it much easier to do the test and troubleshooting, not only in the science enclaves that we put per sonar boxes in, but we've put it at every 1 gig and higher connection across the network. So there's about 70 of them across the infrastructure. And that gives us the ability to troubleshoot much faster. We can segment the network very quickly. We can do proactive testing across the network, and we collect the data and we can look for degradation. So if there are soft failures or equipment that's beginning to fail but hasn't crossed a threshold of an alarm, we can identify that based on the performance. We've also put data transfer nodes out in the network. So we've got one on the East Coast, one on the West Coast, and one in the center of the US. And that is there for researchers to test to the data transfer nodes so they can benchmark. And so they can test the data transfer node, then they can test the final destination and see if there's a change in performance. It helped them with isolating where that issue might be. Another thing that we're trying to do with building this ecosystem is develop a community knowledge base, trying to exchange information that we've collected, not just from Esnet staff, but also from the broader community, and we've been collecting it at the website fasterdata.es.net. Some of you folks are going there now. We get about 2,000, 2,500 hits a week on that web page, and there's some good information there for wide area transfers. But if you have information that we don't have up there, let us know. We'll put it up there, and we'll continue to build this knowledge base for the community. And also, we're trying to develop a feedback loop, not just with the scientists that we work with, but also with other networks. And we're trying to leverage the web as much as we can. And to do that, we're developing a portal that we're calling My Esnet. And the idea there is that people will be able to log in with Shibboleth or OpenID, and they will get a personalized view of kind of like an iGoogle concept, where you have different widgets, and you can personalize it for what you're interested in seeing. So if you're a site administrator and you want to see what traffic is coming into your site, you'll be able, with the authorization, to see a personalized view. You can look at your total traffic, or you can drill down into the individual network interfaces and see the traffic come across those. We're also going to have the ability to initiate per sonar tests through this portal to different destinations in the network. Services-wise, you're going to be able to go through this portal and make an Oscars reservation if you want. You can get a certificate that we offer for like the DOE grids. You'll also be able to log in and initiate a ticket, or get an update on the status on an existing ticket. And based on the attributes, you'll be able to see your ticket, but not everyone else's. We'll also have a discussion forum or idea repository for the community to post ideas. If someone says, hey, it'd be really great if Esnet did X, they can post that there and give us a sort of feedback, or tell us where we screwed up. And again, the knowledge base that I talked about, we're going to continue to build that there. And if there's any ideas or thoughts that you guys have, please let us know. We're happy to share everything that we develop and learn. And if there's something you guys are doing that's really good, let us know, because we don't want to reinvent the wheel if someone else has already done it, and we can adapt it. So that's my last slide. Again, I encourage you to look at the knowledge base if you haven't at Faster Data. And if you're interested in reading the paper about some of the lessons learned on deploying hybrid networks and bandwidth on demand, we've got it a link right there at our blog post. So thank you. Any questions? Yes.
Hello. Hi. Within Europe, we have a performance database, knowledge-based system ourselves, which is called EduPERT.
Okay.
EDUPERT, and that's on the Géant page. There's a link to the wiki there. Have you looked at collaborating, or were you not aware of this knowledge base?
I wasn't personally. I wouldn't be surprised if my engineers know about it. But that's a great idea of collaborating. If there's something there, we're open to sharing it. Definitely. Thanks. We'll check that out.
So, is this version of OSCAS also taken up by Internet 2, or does it interoperate with what Internet 2 has? And how do you get to the university? Because there is typically a network between you and the universities.
So the Oscars that we've developed, Internet 2 is currently running Oscars.5.3 in their ION service. They are currently doing a project called DINES, which is to deploy this virtual circuit service through the regionals to, was it about 40 campuses? Fewer, about 30 or so. And so that will be using the Oscars.6 code. So that'll be new, and then they'll upgrade the rest of it. Sure.
The Oscars 0.6 is actually building backward compatibility to 0.5.3. So if there are installations out there with 0.5.3, the backward compatibility is built in. So people don't have to move to 0.6 in order to interoperate with an older version. Go ahead.
And the communication between the different OSCARs, that is becoming NSI compliant?
That is a long-term plan. I just don't have any dates.
So that will probably be Oscars.7 is the NSI compatible, but we haven't engineering committed anything, as Inder said.
In the morning talk from Johnny, it was mentioned that what he said, the religious wars between packet and circuit switching are decided, and it's packet switching now. From your experience with Oscars and with the amount of usage, you would not agree with him, at least for certain environments, I assume.
Well, I would say that we don't have any religion either way. I think that Oscars has served us very well in a 10 gigabit environment with constrained resources, and so when you have flows that can, large elephant flows that can squash mice flows, Oscars has served us well. We're moving to 100 gigabits, and I think that we'll see how it works in. But we do plan to run Oscars over the 100 gigabit network that we're going to be rolling out next year, later this year and next year, and then we'll see.
Don't forget topology on demand.
That's true. Yeah.
You can't do that. It doesn't matter what kind of network you're in. You need a control
Right.
plane to do that.
Right. So, any other questions? Great.
Okay.
Nope.
Well, please don't forget. Oh, one more. And in the meantime, don't forget to fill out your evaluation form also, please, for the session.
Just a quick question, really, put forward to you. You said that the scientists often have to do it themselves. We don't expect them to become network experts, which is true, because if they were, then we'd be out of a job ourselves.
Yeah, good point.
We often don't know. I'm from a scientific background myself. I did a chemical physics PhD and worked in a lab and had to do my own sort of networking and IT stuff. What's the best way for the campus IT people to actually engage with their scientists on campus to find out what they actually really want? Because what they think they want is often different to what they really want or want delivered to them.
Right. So what we've been doing, and this has been evolving over a couple of years, is we hold network requirements workshops, and we at DOE, we have the DOE program manager invite the scientists in and some of their network administrators to a meeting with us, and we start by having them give us short white papers on what their science is and how they expect it to evolve over the next 5 to 10 years. We don't ask them how much bandwidth do you want or what services. We just listen to what the science is that they plan to be doing. And then out of that, we aggregate, we do it by community specific. So we'll bring the high energy physicists in. Next time we'll bring the climate scientists in or nuclear physicists in. We do them individually, and then we aggregate it, each one into a report that we publish on the website of what we've understood, their needs to be. But we specifically don't ever ask, how much bandwidth do you need, because we found that scientists will take what they think they know and double it or triple it, when they tell it to us, just because they're not quite sure that it'll work when they get it. So that's worked pretty well for us, but we're always trying to find other ways to communicate with the scientists that can help us. And so the other thing that we're doing is we are currently looking to hire what we're calling an outreach coordinator, who will work directly with our network engineers in reaching out to the scientists on the campuses to try and improve that dialogue, because those workshops are great, but we can only do 2 a year because the reports themselves are 50, 60 pages. So we're looking to do that as well. All right, thank you.
Okay, thank you.
Turn this on.
I think they do that. Yes, yes, perfect. This is yours?
No, I think from the how old is the resource development for external contributions or collaborations?
It's open source.
Yeah, but the source is open source, but the team itself works in an open source environment.
Yeah, we've given it to the Brazilians. Norginet's got it. They're deploying it, and we've been